All right, next I'd like to talk about the Earth's magnetic field and its relationship to our atmosphere. As it turns out, we have an atmosphere that is protected from harm from the sun by our magnetic field. So a magnetic field is produced by moving charged particles in the core. This motion in the core is caused by radioactive decay of heavy elements. And so, in a very real sense, the inner and the outer core of the Earth is kind of like a nuclear reactor. What does a nuclear reactor do? Well, a nuclear reactor it has in its center a nuclear core, and that's the source of the radioactivity. Then surrounding that is water. And then that water is heated by the radioactive core. Then that water can be heated and turned into steam. Steam can turn turbines and generate electricity. That's how Diablo Canyon works. So our source of heat in the interior here also heavy elements that are tending to decay by breaking apart into smaller elements. And so in the process of doing that, they release energy. And that energy drives these currents in the Earth's outer core. Okay, and so our core, the inner core is solid, but the outer core is liquid. They're both made of metals. That can conduct electricity, so electrons can move around. So the motion then of all these charged particles in the Earth's outer core is really being driven by all of the radioactive decay that's in the inner core. So the inner core is kind of like the nuclear pile, the uranium that's in a nuclear power plant, and the outer core, these liquid metals, are kind of like the water that's being heated by the nuclear core in a nuclear reactor like Diablo Canyon. And so these motions then produce the Earth's magnetic field. And so to try to understand that better, you need to take a physics class, but we can just state for a fact here that a moving charged particle produces what we call a magnetic field. Now, the magnetic field of the Earth looks very much like the magnetic field of a bar magnet. You may have seen this before, where you have a north and a south pole of a bar magnet, and you sprinkle iron filings on this. What you end up getting is a certain characteristic pattern. This is called the dipole field of a magnet. And so we see the Earth, even though it doesn't have a bar magnet in its interior, has motions that are occurring in the outer core, driven by the release of heat from radioactive decay, that makes it act as if there were a magnet in there. And so why is that good? Well, this is important because the magnetic field can deflect high energy particles from the sun. And these high energy solar particles are called the solar wind. Is this significant? Well, yeah. On the surface of the sun, we get something like 1 million tons of charged particles every second being evaporated off the surface. And so those high energy particles then move along until they get near to the Earth, and then the Earth's magnetic field deflects them. It's like a umbrella, a magnetic umbrella that protects the Earth from direct interaction of these high energy particles. The high energy particles are coming in with a more direct line, then they tend to spiral along the magnetic field lines and produce what are called the aurora effects. So the aurora, sometimes also called the northern and the southern lights. And so this is where the magnetic field of the Earth deflects the charged particles so that they ionize the Earth's atmosphere up near the poles. And so as long as you're away from the poles, then you don't have to worry too much about this radiation. And so this is significant for a couple of reasons. The significance, one, is that, and this is first and foremost, I think, is that this prevents the Earth's atmosphere from being evaporated. So that's a pretty big deal. If the Earth's magnetic field weren't there, then the particles that were in the atmosphere would gain so much energy from these collisions that on the average they'd be thrown right out of the gravitational field of the Earth and they would never come back again. And so the atmosphere would be gone without our magnetic field acting as a big umbrella that shields the Earth from these high energy solar wind particles. And the second very important influence here, of course we wouldn't even be alive without the atmosphere, so this one is of primary importance. But of secondary importance is that this reduces by a large factor the amount of radiation that hits the Earth from the sun. Now, this isn't to say that we don't want any radiation, because mutations happen because of mistakes. And a lot of the mistakes that happen in the genetic DNA reproduction process are favorable mutations that allow for evolution. So you want a little bit of radiation, that's okay, but you don't want too much. If you just have floods of radiation coming in from what are called solar flares, then that's too many errors for the body to be able to deal properly with it. And so that would make life as we know it very, very difficult for life to survive under the influence of such a high energy environment. Now, the Earth's magnetic field occasionally switches polarity. This happens because of random motions in the core that 5 times in the last 5 million years the Earth's magnetic field has changed polarity. Meaning that right now, this is the south pole of a bar magnet, and this is the north pole. Where this is the north geographic pole, but it's the south pole of a bar magnet. And the south geographic pole is near the north pole of a bar magnet. But when this change in polarity happens, it often takes a few tens of thousands of years to complete. So we get a lot of radiation while the magnetic poles are shifting. And they're changing from north to south or south to north. And so we believe that this could be where accelerated evolution takes place, where we get a lot of mutations happening in a relatively short period of time, maybe only, say, 50,000 years. And then those mutations can take hold, and then you have more stability so that you don't have that kind of chaos happening inside of the cell all the time. You just have it happening during the magnetic field reversals, which can then cause accelerated evolution. So this is a theory. We'll say it may cause accelerated evolution. By creating more errors in the genetic profile. And some of those errors we suppose would be favorable, whereas the majority of them would probably be unfavorable. And so the Earth's magnetic field then seems to be very closely associated with life. Certain types of magnetic-seeking bacteria are able to find their direction by using the Earth's magnetic field. And various kinds of birds are able to. It's thought they even have maybe a little viewfinder in their retina that is like little crosshairs that are telling them which way to fly and are showing us what direction is north and south. And so these magnetic field properties of the Earth are very special and very, very important. When we look at the other planets in the inner solar system, none of the other planets have a strong magnetic field, only the Earth has a strong magnetic field. In the inner solar system. In other words, Mercury, Venus, and Mars, our companion inner worlds, do not have strong magnetic fields. Now, Mercury and Mars have lost their heat long ago because of their smaller size. Venus, though, is more comparable in size, and so we might wonder, well, if Venus has the kind of heat source that the Earth has in its interior, then why wouldn't it have a magnetic field? And the answer, we believe, is that Venus is rotating very slowly in its axis. Venus takes longer to make one turn on its axis, something like 245 days, than it does to go all the way around the sun, which is only about 225 days. So with such a slow rotation rate, we think that that is the reason why Venus doesn't have a strong magnetic field. And so this is something then that we should be grateful for. It keeps our atmosphere in place. And so we wouldn't be talking about meteorology without an atmosphere. And so the magnetic field is really our first line of defense in protecting the Earth from the hostile effects of the sun. That being said, the sun does exert its influence on the Earth. And so the sun's activity levels change over what we call an 11-year cycle. And associated with this, we have sunspots. So at the peak of the cycle, we have the most sunspots. Then, maybe 5.5 years later, we have very few sunspots. Then another 5.5 years later, we go to more sunspots again. And so if we plot the number of sunspots versus time, we get a peak level and then a minimum level, another peak level and a minimum level. Sometimes the peaks go up a little higher, sometimes down a little farther, but always about 11 years between peaks. Now there are some variations in this that were observed back in the late 1700s and early 1800s where there weren't any sunspots for something like 30, 40 years. And this was associated with a mini ice age in Europe and also with very, very cold temperatures in the United States. When George Washington crossed the Delaware River in a critical battle during the Revolutionary War, he attacked the British on Christmas Eve, and he had to fight his way through a tremendous amount of ice that had completely covered the Delaware River. If you look at the Delaware River today, you see no ice whatsoever. And so it may be a coincidence, but it's possible that these levels of sunspots are associated with our weather. And when we get more sunspots, it's been observed that we get more solar activity. Not only does the sun produce more radiation, but there are more solar storms. Which could sometimes be called magnetic storms. Because the source of the sunspots is actually magnetism. If we were to look at the surface of the sun, and this isn't really what's happening, of course, but it's almost as if there was a little horseshoe magnet that was beneath the surface of the sun. So associated with that magnetic field, you would have a sunspot pair. And so each of these little magnetic storm activities would produce a sunspot pair, and then this arching structure here would be filled with particles that would be trying to escape and be recycled. So these arching features above sunspot pairs would be called prominences. But every now and then, the lines of the magnetism cross over. And so irregular sunspots can give rise to solar flares. And so these solar flares are when the solar wind particles can increase by a factor of 1,000. And the particles then can be ejected, and they can just escape at very high velocity so that the solar wind can increase by a factor of 1,000. This can overwhelm the Earth's magnetic field, which is doing its best to stop this. But some of the radiation gets through. And so when solar flares occur, this can cause blackouts on the Earth. And would expose any astronauts that are in orbit to a lethal dose of radiation. And and could knock out power, even worldwide, it's possible, if the solar flares are big enough. There was one solar flare back in 1859 that we believe that if it happened today, it could knock out the world's power for as much as a couple of years. And if everything went down, it would take much longer to bring it back up. And so the Earth's magnetic field does help, but this is the most extreme situation then, when we would have highly active sun. And this would happen when there are more sunspots. So this means you would get more solar flares. Okay, and so what does this tend to do then to the Earth? Well, when we have more sunspots, we tend to get more solar radiation, and that causes the temperature of the Earth's atmosphere to increase. And so with all of these flares and with this increased activity, this heats the atmosphere a little more than normal. But a heated gas will expand. And so the Earth's atmosphere actually gets bigger during a peak of the solar flare activity. The Earth's atmosphere rises. And also, when we have sunspot maximum, it's been determined that there are more electrical storms. Worldwide. When we have a peak in the sunspot activity. And so this was first discovered back in the early 1970s when we had sent a space capsule up to study the sun. And so we put it up at an altitude of about 150 miles, which was well above what we felt would be the top of the atmosphere at that point. And we were getting ready to study the sun when it went into its next sunspot maximum cycle. But ironically, the sun heated the Earth's atmosphere up, and that caused the atmosphere to rise up above the level where the space capsule was taking data. And that caused atmospheric drag, which caused the SOLARMAX telescope to crash and burn. It was destroyed by the very effect that it was trying to measure. And so now, with, say, the Hubble Space Telescope and with the International Space Station, and before that with the Space Shuttle, we try to keep these objects up an extra 20, 30, 40 miles higher than normal, just if they're going to be up long enough to encounter a sunspot maximum, because we know that the Earth's atmosphere can rise up at those times and create more atmospheric drag.